So first of all, it's a great pleasure to introduce Finn. I actually saw this grant during the anonymous days of COVID grants that we all got to review the many.
Oh, you were reviewer 3?
I was the reviewer, yeah. So it'd be lovely to see how this work has actually delivered on what you said in the grant thing. So welcome to ACE2 and pigs. Thanks, Finn.
Yeah, just to forestall all that, yeah, it was a terrible failure, and this will be a very short talk. No, so this was a project that was very much born out of the lockdown, and it came from kind of asking the question what it was that as an institute we could kind of contribute to the research with SARS-CoV-2. Obviously, we could look at trying to make vaccines, but, you know, competing against the big guys, that probably wasn't going to work. Same thing for antivirals. And so one of the things that Rosalind does pretty well is to make transgenic animals, specifically in livestock. So I'm going to be talking about the project we did along those lines, and I'll go into a bit more detail about why we think making a transgenic pig was a good idea for a large animal model. First of all, though, really need to kind of highlight the fact that, I know it's kind of a corny term, but this genuinely was a case of team science. This wouldn't have been a possible project without the different expertise of a number of individuals and groups across the two institutes, both the Rosalind Institute and the Morden Institute, which is just down the road from us. And I'll try and remember and kind of bring up the various people who contributed at critical times of the project. So, as we're probably all aware, animal models have played a crucial role for helping us to understand the pathology caused by SARS-CoV-2 and also in the development of vaccines and antivirals. And there's a number of different animal models. You've got the rodent models, most prominent of which are the human ACE2 mice, and more recently the hamsters have become very popular. Also, you have ferrets that have been a useful model for looking at airborne transmission. And then non-human primate models are obviously the closest models we have to humans. And each model has advantages and disadvantages and have all sort of contributed. One of the things that we still don't have, or at least didn't have, is a large animal model that recapitulates a lot of the hallmarks of moderate to severe disease with COVID-19. So this is why we kind of initially suggested the use of pigs as a model for COVID-19. Pigs tend to be very good for respiratory models of human diseases, and that's for a number of reasons. One, the anatomy, physiology, and genetics are closer to humans than they are compared to rodent models or ferrets. We have good molecular tools for pigs, and as I kind of briefly mentioned, we also have facilities which are particularly important for this project to be able to do challenge studies at CL3 levels, at containment level. And compared to non-human primates, they're less expensive and have less ethical issues associated with them. And that being said, as I mentioned, all animal models have pros and cons, and so it's important to recognize the limitations of these, and obviously to say that, you know, we never see it as replacing the other animal models, but more kind of contributing to overall tools that we have. Compared to rodents, they're obviously a bit more expensive, take longer to make. Doing the challenge studies are more difficult, so you can't do quite the same number of animals compared to rodent models. One of the biggest barriers, though, straight away, was the fact that early studies showed that the pigs were not susceptible to SARS-CoV-2. And the idea we had was to try and make transgenic pigs that express human ACE2 to overcome this barrier. However, we didn't know for sure whether doing this would actually work, because there could have been other barriers to infection. And even if we did manage to make the animals susceptible, we couldn't be sure whether they would then show the same kind of signs and hallmarks of disease in humans. And that's really the important thing in an animal model and what we wanted to sort of recreate. So obviously a lot of work went into actually making the transgenic animals. I'm not going to have time to go into that. Essentially, just to summarize, the approach that we took was to use a lentivirus delivery to zygotes. The lentivirus was expressing human ACE2 driven by the K18 promoter. This is the same promoter that was used to make the mouse models. And then the zygotes were then introduced to surrogate pigs, and the hope was to generate the transgenic piglets. Now, there was a lot of reasons and discussion about which was the best approach to take. Essentially, we took this one because we had the highest confidence that we'd be able to generate the transgenic pigs this method, and we also thought it was the most likely one to give us susceptible animals. So that was the reason going for it. And it took us from scratch about a year to make the pigs, so it was quite rapid, and we were a bit lucky. It worked first time, partially luck, but also down to the skills and expertise of Simon Lilko, for example. He's the expert in transgenic pigs, and also the team down at the LARIF, which was the large animal unit who did the surgeries. So we managed to generate the pigs, and we characterized them and showed they expressed human ACE2, so that was all good. And so the next question was really coming to the crux of the matter. Are these pigs susceptible to the virus? So around about last September, we were able to transfer the pigs over to the Morden Institute, where they have the high containment facilities. And again, there was a lot of work that went into actually enabling us to do these challenge studies, the licensing, a lot of the paperwork, and David Griffiths and Tanya Presnick were key in getting this sort of established. And the design of the experiment was we were going to infect with an early strain of SARS-CoV-2 called Edinburgh 2. The containment rooms down at Morden could hold around about 12 pigs of that age. So this sort of determined the size of the experiment we were doing. We divided those into 3 cohorts. Each cohort had 3 transgenic pigs and 1 wild-type non-transgenic pig. Although they weren't related directly to the transgenic pigs, they were similar in genetics and age. And the length of the experiment was going to be 7 days. We would like to do longer, but again, this was proof of principle study, so that's what we chose. And then at days 2, 4, and 7, we would euthanize the pigs. We would also do lateral flow tests to see if they came up positive, and the pigs were monitored twice daily for temperature and clinical signs. Once the pigs were euthanized, we would take tissues to test for virus levels by RT-qPCR and also TCID50, and then also take tissue for histology analysis. So the main question at the time was, did it work? And to be honest, at the time, I wasn't so optimistic. I've been kicked in the head enough times in science that I'm somewhat cynical. The guys at Morden were sort of more optimistic. But the first test, really, the first way to find out was, luckily, we had lateral flow tests from what had been developed to monitor humans, and they would, we figured work quite well with the pigs. So it was David Griffiths that actually first did this experiment because he was in the CL3 containment unit at the time. And for once, we were actually happy to see 2 bands on a lateral flow test. So here you've got the wild-type pigs that we wouldn't expect to be susceptible as based on previous experiments. But then all the other 9 pigs tested positive by lateral flow. So this was an early indicator that what we were seeing was successful infection. The next question was, well, do the pigs get sick from the infection? And the answer is yes. The first sign of this was that they developed fever. This is just showing the temperature here and an example of some of the pigs. Here are the wild-type pigs showing no signs of fever. Anything over 40 is considered fever in the pig. So some of them really spiked quite high with the fever. And all apart from 1 pig that was euthanized at day 2 all had fever. So that's a pretty good indication and matches up with human infections for COVID-19. In addition to fever, we also saw coughing, sneezing, respiratory distress, nasal discharge, malaise, and loss of appetite. So all kind of symptoms that you, or clinical signs that you would associate with COVID-19 infection in humans. We then went on to test the tissues for virus replication and levels of viral RNA, and you can see high levels in the nasal turbinates, in the trachea, and in the lungs, so both in the upper respiratory tract and the lower respiratory tract. Levels of virus RNA was lower in the lungs compared to the other two tissues. Again, this kind of resembles the kind of infections you see in humans. And we also could recover infectious virus. We could only recover it from the nasal turbinates, and it peaked at day 4. The likelihood is that there is infectious virus in the other tissues, but the TCID50s are less sensitive to the RT-qPCRs. However, it shows that there's robust replication of the virus in the pigs. So the other key aspect we wanted to look at was the immunopathology in the lung, because that's really what's associated with definitely moderate and severe infections in humans. And this was based on work by Tanya Presnick and David Dorwood, who are the pathologists. But you don't really need to be an expert pathologist to see the difference between the wild type and...
10 minutes.
That's 10 minutes?
Yeah.
Okay, grand. You can see here, this is the wild type lung, and this is the from the infected animal. And it's lost all this air spaces, has massive inflammation, infiltrates, and this is called hepatization because it makes it look like liver. There's also a number of other aspects that look similar, such as inflammation. We've got fibrin deposition, edema, and just to point out here, we also saw blood clots that was also associated with severe COVID in humans. And we got seroconversion in one animal, and I'll skip over. One of the key questions was whether we got association between the levels of human ACE2 expression and pathology, and it's a difficult and complex question to answer, so I'll talk about that afterwards if anyone's interested. So essentially, we've made the animal model. It pretty much ticked all the boxes we hoped for. We're now looking to use this for things like vaccine testing and antivirals. And this is everyone that helped, and this is me in a spacesuit. That was quite fun. Okay, thank you very much.
Thanks, Finn. That's awesome. We've got time for questions. Miles.
Great to see the data. Obviously, everybody was disappointed when pigs couldn't get infected in the early days and the WHO calls that I was on. So I led some of the work when I was at Porton-Down, all the non-human primate work, and of course, for many reasons, pigs would be a great backup. But with the pathology that you're seeing, it does seem to be more severe than we published in non-human primates, but where we really had a big advantage, we had a fantastic veterinary pathologist, Javier Seguero, who had put a metric on that scoring of the lung. So showing pictures to non-pathologists, we just say, oh, it looks different. But if you can actually gradate that, then you can look at the efficacy of your therapeutics, vaccines, etc., going forward. So maybe we could, look, I talked to Javier, but it's read our papers and get that. And you chose day 7 based on what?
Day 7, as in...
Day 4 and day 7 is your cull dates to
2, 4, and 7,
yeah.
Yeah, I mean, you know, we would like in the future to go longer because obviously, you know, the second week can be critical in humans for pathology. So, yeah, it would be interesting.
But in the NHPs, we saw that it was all gone by day 6, day 7. So we culled, that was our own day. We left it to day 14, and it was recovery, and you didn't get these fine detail then of the pathology.
We still saw pretty severe pathology at day 7 in these animals, yeah.
Okay. Thank you.
Anya. Go on, shout. You can shout.
Did you see evidence of regeneration at day 7, like you see in hamsters but not in mice?
As in regeneration, as in healing of the lung?
Type 2 pneumocyte hyperplasia, bronchial epithelial cell hyperplasia. Paul would have told you. It's also pathology.
Yeah. I come back to the idea that I'm, you know, the team science, and I'm really not a pathologist. Yeah, I would probably have to ask David if he saw that. It was difficult to score the pathology, coming back to that, because we didn't inflate the lungs. Again, due to the fact that it's difficult to do in CL3 conditions and difficult to do with pigs, and it makes it harder to interpret the pathology. But
I mean, there are different approaches to quantify, and it's only there's a striking difference between mice and hamsters and the lung, because you said in your primates on day 7 it's down in oval antigen, and the hamsters is like that, and they start to replicate the damaged epithelium and to grow again, but mice don't do that. That's why I asked the question.
yeah, I can talk afterwards, and then I'll furiously be typing to the pathologists.
So, Finn, I've got an easier question.
Oh, thank goodness.
So, two really, just quickly. So, Miles's monkeys were young monkeys, and we know severe disease in humans is associated with gentlemen of my age and older and of a certain size, right? Those are your 3 risk factors.
Yeah.
Can you model that in your pigs? In other words, the more unhealthy the pig, the worse the disease it gets. And some thinking of James's mice, do you see SARS-CoV-2 in the pig brains? Because do they have ACE2 in the brains as well?
We haven't looked in the brains. We didn't see any signs of neurological aspects. We have taken some tissue from one of the brains of the animals, but again, coming back to working in CL3, the idea of trying to get into the brains was tricky. The disease models, one of the things we'd be keen on is crossing these animals with obese models of pigs, diabetic models. The aged ones, that's going to be trickier to keep pigs that long to test whether age has an impact. Dal?
Dan, last question, Dan, and then we'll move on.
Thanks, Vin. That was really interesting data. I'm surprised by the results, and I think maybe from the same angle that you might have been pessimistic about them before. But so, if I understood correctly, pigs that are sort of wild-type pigs, when they're challenged, there wasn't much disease or any sign of infection.
None.
We've shown, and I think other people have shown, that pig ACE2 is used well by these viruses, and yet I guess you would assume then that there's some post-entry restriction factor, but you put human ACE2 into these organisms, they're then permissive to infection, given a disease that looks like COVID. So it kind of smacks that there's something different about porcine ACE2 distribution than in other susceptible animals. Is that roughly what you're thinking? Or?
Yeah, I think if you did the same experiment with porcine ACE2, you'd probably get similar results. Potentially not with later virus isolates, but certainly with the earlier ones. And they know that they have looked, and expression of ACE2 is lower in the upper respiratory tract than in humans.
Right, I'm going to hurry you off now, and you can discuss it over bacon tonight.
Yeah.